Okay, uh, welcome to our 4 o'clock session on PTP management and media flow monitoring. One of the reasons, and the presenter, of course, is Thomas Gunkel from Skyline. We've talked about how PTP works. We've talked about how you can use PTP to synchronize media flows. Now we need to talk about how we can manage those PTP signals and monitor them in our network, along with all the other media signals. How can we tell that our systems are really doing what they need to do? So that's what we're going to hear about. Thank you very much.
Thank you. Good afternoon. Thanks for the introduction. My name is Thomas. I'm working for a company called Skyline Communications. For those who don't know us yet, Skyline, a company, independent company, founded in 1985. We are headquartered in Belgium, close to Brussels. We have about 300 people working for us. We have a global presence with about 20 sites internationally. What are we doing? We do end-to-end monitoring and orchestration. The name of our product, you might have heard that, is called Data Miner. What it actually is, it's an off-the-shelf network management system, multi-vendor, that's important, and an OSS platform as well. To monitor, to orchestrate, to control complete media ecosystems. And a subset of that, obviously, is media flows PTP. That's something I want to talk about today. Just to give you some numbers in terms of integration, what are we doing? We have about 6,000 systems being out there in the media industry. We have about 5,500 drivers, means integrations with all kind of vendors and systems. Could be hardware, could be software, could be some virtualized environment today. Let me start with PTP. PTP is essential in an all-IP infrastructure. It will replace the black and burst signal, but why do you monitor it? PTP is a protocol. It's not a signal anymore like black and burst was. To let you know why it's not always so easy to deal with PTP, PTP, the standard, makes first of all some assumptions. An assumption in the network, there is no packet delay variation, no PDV. There is no asymmetry. That can be internal asymmetry in a switch from ingress to egress, but also network asymmetry during the transmission. And the other assumption is PTP timestamps, they're always perfect. But obviously, everybody knows that's not the case. So PTP as a protocol always has mechanisms already built in to alleviate those sources of errors. What are you doing to do timestamps in a proper way? Do them in hardware. This is most of the applications we see. PTP Grandmaster today, that's not done in software, you do it in hardware. Use quality of service to prioritize your PTP traffic. That's very essential. Otherwise, your media streams or other traffic might take over. And then PTP has a lot of capabilities to set it up properly. There is boundary clocks, transparent clocks, end-to-end mechanisms, peer-to-peer mechanisms, timing intervals. So a lot of things you can tweak PTP, a lot of settings you can do to optimize the precision of time at the input, at the endpoint. That's really what you want to do with PTP. But again, the world is not perfect and things go wrong. And what is going wrong, I want to show you quickly common sources of errors. In PTP, we see a lot of projects we recently have developed in 2022-6 or in the 2110 world, where things go wrong during the configuration. PTP is not too simple to configure. You have the Grandmaster, you have your boundary clocks, maybe transparent clocks, and end devices. And every single device has to be configured individually. Your BMCA settings, the best master clock algorithm settings, they have to be the same on every single device. A very simple example is the domain number. If you have 5,000 devices talking to each other, that single setting has to be deployed to every PTP-aware device. Your priorities, there's a lot more to it, but also the messaging rate intervals, sometimes people forget about it, like sync interval, announcement interval, also the timeout intervals, you have to make sure those are the same in your facility. The communication mode is another example, can be unicast, can be multicast, can be mixed mode. Again, plenty of capabilities, how to set up PTP, plenty of things that can go wrong. What are we doing here? We really try to automate that complete process. To automate PTP configuration, not to do this manually anymore, that's error prone. You want to automate it. When you do that, less things go wrong. The other parts is then when it's up and running. We might see device issues. A Grandmaster can fail. A boundary clock can fail. A loss of external reference. You lost your GPS, for example. But also we see, and that's interesting, in real projects, some devices, they haven't implemented the BMCA algorithm in the best way. There's still some work to do for some manufacturers. And when this happens, the algorithm sometimes might kick in and strange things happen that should not happen, but in reality they do. And then obviously the third thing, network issues. Event messages might get lost, they might be missing. Sometimes they are corrupted. You see increased packet delay variation over a certain boundary. The network is not symmetric all the time. You see asymmetries. Also, pretty often we see issues with multicast traffic, especially when you run PTP in mixed mode. You have a mix of unicast messages and multicast messages, and those sometimes cause issues. Multicast typically creates a little bit more issues than unicast traffic. What to do here? Once you have set it up in a good way, the way PTP works, it can still do weird things. You have to constantly monitor and control the PTP configuration across the whole ecosystem. How do you do that? First of all, I want to quickly show you what we do with PTP provisioning. We have a tool set called infrastructure discovery and provisioning, and it comes together with finding your infrastructure in the network. That's the first thing. You want to automatically detect new devices in the network, also the PTP aware devices. That can be done, excuse me, via multiple mechanisms. ISO 4 is one of them, but still we see a lot of products, they don't support it. So you need to have a tool set, a platform to also support proprietary protocols to be future-proof and to make sure you can detect devices automatically today. That's really the first step when we deploy those projects. Then automatically extract the PTP topology, not only to find new devices, you also have to know where they are in the network. There you can use protocols like LLDP, something we have implemented for a customer recently. And next step, once you know where those devices are and who those devices are, you want to apply your standard default settings. That might be the PTP domain, priorities, the intervals. You might have golden configurations, and you apply them automatically to all of the PTP-aware devices. And last but not least, compare PTP configurations. Another topic, when you have two grandmasters, 90% of the values might be just the same, but a couple of those values, like the priorities, they are different. You have to make sure to compare those as well, just to see if the setup is okay, if you have done it correctly. Otherwise, you would only find out that something went wrong when a PTP grandmaster takes over and you have a failover situation. The second part, once you are done with the setup, don't forget about it. You still have to monitor it constantly in real time, 24/7. It's a real-time system. It has the BMCA algorithm built in, and there things can happen at any time. What are we doing? We monitor every single metric on the grandmasters, on the PTP-aware devices, the boundary clocks, the transparent clocks, but also the slave devices. Even more important those days, monitor the PTP performance over time. We see situations where the network slowly degrades. When you only look at your system health state at a certain point, you would not necessarily realize that you have certain network degradations over time. That's important. Values like PTP offset or mean path delay, we monitor typically over time to see some degradations in the network, and you can start reacting before things go really wrong. Also monitor the PTP multicast traffic, not only your PTP settings, but also the multicast traffic. Therefore, we can integrate with network analyzers to really look into the packets. But at the same time, we talk to the switch fabric via the native APIs to get routing tables, snooping tables, or the unicast traffic to see what's going on in there. If the PTP traffic really shows up where it should show up, or sometimes the other way around. We see also multicast traffic where there should not be any multicast traffic. Last but not least, again here, we talk a lot about PTP security. We see some devices that don't work perfectly well. We have to apply some security workflows on top of it in certain situations. One of the examples I can give, we see PTP slave devices. According to the standard, to the specifications, they should have a slave-only mode, that they never announce themselves as a new grandmaster. But we have seen devices all over a sudden, they announce themselves as a new grandmaster. That's something you don't want to do. If the device is not capable to avoid that, we can talk to the switch fabric, for example, and block those announcement messages. With that, you have a easy and nice to implement solution to block that, to make sure a slave device will never become a new grandmaster. Let me give you a couple of slides on screenshots, overviews. How do we do that? Typically, we have those visual representations on the complete PTP ecosystem. Shows you how many PTP-aware devices do you have, shows you who's the active grandmaster, shows you my BMCA values, my priorities, but also the actual messaging rates and probably PTP related events. When there is a change, device changes from master to slave mode, or there is a new PTP-aware devices, you want to see that. One single user interface to give you the full overview on PTP. Also some measurements you can do here, the performance monitoring, that you can see how the system behaves over time. Then you can go into details. People want to see the PTP topology. If the switch fabric supports LLDP, that can be extracted automatically, so you don't have to do anything. We show that. We show PTP-related errors to it. We would not show an error when a power supply fails here. That's really only for PTP. People want to see if the PTP health state, the PTP ecosystem is doing well, or if there's an issue. And also an indication of who's the current grandmaster for that customer. That's another example on how we compare PTP configurations. You see those green and not a single red indicator. That means all the values that should be the same, they are the same. And those values, they should be different, like priorities, they are different. So the configuration is okay as it should be compared to my golden configurations, compared to my golden profiles. Another one on a switch, just to give you more insights, the basic KPIs, but also PTP information on every single Ethernet interface. When you run a PTP switch in boundary mode, there's a lot of configuration work to be done. Every single Ethernet interface has to be configured with the messaging rates. And some switch vendors, they also expose a lot of PTP statistics, which is very useful for us, like the amount of messages you have received, you have sent. You can get a really good overview on your PTP ecosystem. And then you can go into more details, like this one here, where you see trend graphs on an offset from a master over time, and you see potential network degradations as well in a very easy manner. So once you're done with PTP, most important for us, that's always the first thing we look into when we do those projects in all IP infrastructures. Second part is to track your media flows. Why is that? In the past, you didn't do that. All you had to do, you probably were using your waveform monitor every now and then, and not many things went wrong. But now the world is again a bit more complex. Very obvious, the network is a shared medium. It's obviously a non-linear medium, and you have to run real-time streams over that. That's a different approach. That makes it more complex than SDI was. The other part, in the past we had a single or a couple of SDI routers. Now we talk about complex switch fabrics in spine leaves. We see installations with 50 to 100 switches out there. That's a higher complexity. Then compared to a single SDI signal in the past, we see those 2110 based deployments. You have a video stream, multiple audio streams. In 2022, there's 7. That sums up in trucks, in studios. You easily have 20, 30,000 multicast streams in a single system, in a single deployment. Another part I want to discuss and quickly show you is the way broadcast controllers and SDN controllers talk to each other. An SDN controller today, when we talk about destination-based switching, it needs to talk to plenty of endpoints rather than a single endpoint, which was the SDI router in the past. So again, more complexity. And the other problem we see today, broadcast and SDN controllers, they use, I call it classic router protocols. Let me give you an example here. You have the broadcast controller. Typically, they have databases where you set up your router labels. Like my input 10 is camera 10, my output 20 is my monitor 20. And as an operator, you want to do a switch command from the input to the output. You hit your button on the hardware control panel, and the broadcast controller sends the very same switch command than it did when it was an SDI infrastructure to the controller. That means one command, input out to input 10 to output 20, and that's really it. The SDN controller takes that. In the past, this was my SDI router. Now the SDN controller has another database. The SDN controller knows my input number 10 reflects that multicast address 239 something. My output number 20 is probably a monitor, a multi-viewer, has that IP address. It goes directly to that multi-viewer, sets that multicast address if it's IGMP based. What happens? The endpoint sends an IGMP join, and the ISDN controller immediately might send back an acknowledge to the broadcast controller, thinking it has done all the job, it has fired the command, means entered the multicast address in the endpoint, but things can go wrong, and sometimes, and we see that pretty often, the broadcast controller panel shows a connection. It thinks, because it has received an acknowledge that the switch was made, but your screen stays black. And what are you doing next? You cannot run after the green cable. You need some other tools. You need something to dig into the root cause of what's going wrong. This is why you really need media flow tracking. You have to track your flows, because what can go wrong? And we've seen implementations, that comes back to configuration issues again, that the databases are not perfectly right. You have wrong database entries. That can happen during initial setup when you do it manually. You will avoid that when you use ISO 4, but even in ISO 4 you might have issues in communication. So you might be out of sync. Also, when you replace devices, people might forget to set the right multicast addresses to that device. Then you have a sync problem, the database is out of sync again. And also the broadcast controller often has its own database, and we have seen those being out of sync. That leads also to some conflicts, and you cannot route your streams anymore. Then again, the sources. SDN controllers typically, they don't check the source, they assume it's always active. That might be the case, but you should still double check in a proper monitoring system if the source is streaming, if it's active, if it's streaming with the right multicast address, the one which is set in the SDN database. In the network, IGMP issues, static multicast issues. When we talk about source-specific multicast, that's another layer of complexity, another layer where things might go wrong. And we also see oversubscription in the network. Not necessarily because the SDN controller has done a bad job. More often, people play in the network, people work around the SDN controller, they set up sources manually just for a test, and they forget to turn them off again, and you have more traffic than expected. And the SDN controller might not be aware of that. Then last part is the destination. What we see sometimes, IGMP issues, the join didn't make it, or a leaf didn't make it, or again, the wrong multicast address, which was set by an SDN controller. So plenty of potential root causes that go wrong, or via stream doesn't make it from a source to a destination. So track your media flows in real time. That's also key for us. Next to PTP, that's something new. You didn't have that in SDI. What are we actually doing when we say we do flow tracking? First of all, we read the cross-point status from an SDN controller. We are checking the status, where should all my flows be? And then we start checking that versus reality. Where are those flows in reality? So we get a state from a controller, then we start crawling through the network. Is the stream really there from source to destination? And moreover, I mentioned it already, also find those flows which are in the network but which are not supposed to be there, those leftovers or ghost streams. How do we do that? We have to interface to a lot of different devices. You have to talk to the source, to the destination. You have to talk to the switch fabric and use a lot of different technologies to be able to track your flow in the network. There's an example of an implementation we've done for a customer. The operator, first of all, they want to use their labels. They don't talk multicast typically. They have no idea when a CCU doesn't make it to my destination, when I don't see my camera signal, which multicast address this is. So to have a proper user interface, you cannot use those IT-centric tools. You find them a lot, but for a broadcast operator, he might not be able to operate them. So give them the same labels they have in a broadcast controller. Choose your stream, the one which is not working. Then we immediately start checking the sources. Is that still streaming on the right multicast for main and backup, for my video, for my audio streams, for my auxiliary data streams? Next step is then to extract the network topology, to detect in real time where those streams are, on which interface are those, to detect them, to see is there network traffic coming. Then you already know it's not the source is still streaming, must be somewhere else. Then we checking the SDN controller on the right-hand side. Those are the crosspoint status information from that EVS system. In this example, that should go to 5 destinations. Everything is okay, everything is green. We are checking on the egress side, again, routing, snooping tables. We are checking the destination. We are checking the database information of the SDN and broadcast controller. And if everything is well, you don't see anything in red here. There's no exclamation mark. So that's an example where the stream makes it from source to destination. You can go into more details. We can also extract the individual multicast flows using S-Flow, using NetFlow technology to be sure the stream is really there, not only the interface traffic or the traffic in the interface, but really to the finest details of every single interface in the network. Here's an example when things go wrong. Again, there was a CCU, there was a camera signal, the source is streaming, all good here, has the right multicast address, the right source IP. On the right-hand side, you see a lot of destinations, but one destination didn't get the stream. The situation here was the broadcast controller indicated that CCU made it to that destination, but the stream was not there. It was an issue at the end here in the routing tables. For some reason, it didn't make it. This was an IGMP-based system. Maybe the IGMP joint didn't work out. Giving an operator those tools, they can easily find the root cause. Again, if it's the source, if it's more related to the destination, or if the root cause is somewhere in the network. Not necessarily, I claim they can solve the issue, but at least they know whom to call. Call the specialist on the camera, call the specialist on the destination device, or call my network specialist to fix the issue. As a summary, for us, when we talk about all IP infrastructures, really take care of your PTP infrastructure. Monitor it, manage it, make sure you automate a lot of processes, because this is a very dynamic system. Secondly, things you didn't have before, track your uncompressed media flows in real time, that's important. Make sure you track them all the time. I want to give you one more example. In 2022-7, you still might see your screen being there on a multi-viewer, but you have lost your second leg in the background because the redundant stream doesn't make it anymore for whatever reason. You would not necessarily even realize that you have a problem. So track it in the background, make sure you constantly check if your flows are present or if there is any issue. And last but not least, we call it go for true end-to-end SDN orchestration rather than SDN control. And that's really related to the fact that we also need new protocols. We cannot work with protocols any longer that just fire commands and everybody hopes that it will be executed. Make sure that you have a platform that actually checks everything around it. In the past, that was perfectly fine, that you could just fire a command to your SDI router, it executed, nothing happened, nothing ever went wrong. But nowadays, you have a lot more things that could potentially go wrong. Whenever you invest in a platform, make sure that you invest in a platform that double checks what it's doing. That's what we call orchestration rather than control, which is firing commands to devices only. And with that, I want to say thank you very much. If you have any questions, I will be around for a few minutes. If you want to have a deeper dive, come by to our booth and we can have a chat. Thank you.
Thank you, Thomas. Any questions from the audience? I had a quick one. Just so, what was the most complex PTP problem that you ever had to troubleshoot?
The most complex, I might have to ask my engineers, but one we came across was recently that people had a grandmaster, which wasn't supposed to be a grandmaster. They didn't realize for a couple of weeks that they were running on a bad grandmaster. And the second problem there was they were running on that grandmaster and also the time was wrong. Timing was set to 1970 or something like that. The funny part here was nobody really cared, but then they realized they have a couple of time-stamped licenses. And the failover all the time was set back to 1970 and some of the playout instances. And this project didn't go live yet. They just shut down immediately. They said, no more license, goodbye.
Yeah.
So it was a single issue in PTP, but in reality would have caused going the playout down.
Yeah.
It was not so complex, but it has a big impact.
Yep, exactly.
On the customer.
Exactly. Anybody else Any questions? Okay.